understand the processes that occur in synchrotrons, it is first crucial that you understand how electrons work. They are fundamental particles, meaning they are one of the basic building blocks of matter. They cannot be broken down into anything smaller. Electrons at high energy are able to emit photons, or small packets of electromagnetic radiation. Synchrotrons utilize this principle and are able to isolate electrons and give them enough energy to emit photons, which are then captured and used in subatomic analysis. Their emitted EMR waves are shaped and shortened by magnetic fields to obtain the wavelength required for certain experiments. Electrons start here, in the electron source. Through a process known as thermionic emission, electrons are released by an electron gun and shot into a linear accelerator. Radio waves accelerate the electron once they are inside the linear accelerator. Electrons then enter into the booster ring, where electric fields are used to accelerate them almost to the speed of light, and magnetic fields are used to keep the electrons on a stable trajectory. Once the speed of light is almost reached, the electrons are then released into the storage ring, where they will remain for the next 20 to 24 hours. In the storage ring, particles are no longer accelerated, and only magnetic fields are used to keep them on a stable path. Because the electrons are carrying so much energy, they begin to release photons, which are captured by these beamlines. This captured photon is what scientists are able to use for research and investigation into cells, atomic structure, and any other subatomic inquiry they may have. This is the electron source. In general, electrons are generated by thermionic emission from a hot filament, which serves as a source. This is also known as the electron gun. The electrons are then accelerated through a linear accelerator by a source of radio waves to several hundred mega electron volts of energy. This is the booster ring. The electrons are injected from the electron source into a circular accelerator, known as the booster ring. The booster ring increases the energy and speed of the electrons through the use of the same type of electric fields we studied in Physics 30. They are also kept on a proper and stable path by magnetic fields. The electrons remain in the booster ring until they have almost reached the speed of light. Electrons are periodically transferred from the storage ring to the booster ring when the storage ring current falls to maintain a strong beam current. This is the storage ring. The storage ring is the main component of a synchrotron. Electrons typically remain in the storage ring for 20 to 24 hours, traveling at almost the speed of light, and in that time, they cover a distance 4 times the diameter of our solar system. The energy and speed remains constant in the storage ring, and magnetic fields are used to stabilize the electron and prevent it from colliding with the outside walls or bottom of the storage ring. The main magnetic components are bending magnets, or dipoles, quadruple and sextuple magnets. Bending magnets force the electrons to follow the closed path, and the beam is focused by quadruple magnets. Sextuple magnets serve as a corrector for chromatic aberration. As electrons bend through the storage ring, they emit photons. This is one of the beamlines. The beamlines are placed on a tangent to the bends in the storage ring. Beamlines are used to capture the photons emitted by the electron. The beamlines are designed for specific dedicated applications. They utilize the emitted photon to assist in tasks such as X-ray imaging, also known as tomography, X-ray absorption spectroscopy, near-edge and extended-edge spectroscopy, small and wide-angle X-ray scattering, and X-ray fluorescent or emission spectroscopy. This is one of the magnetic field sources. As the electrons are accelerated in a circular path, they must be kept stable on that path. Magnetic field sources are used to prevent electrons from smashing into the walls of the accelerator or going too high or low in the tunnel. Magnetic fields are used to keep the electrons on a proper path in the middle of the storage and booster ring. Particle accelerators use electric fields to speed up and increase the energy of a beam of electrons. Electric fields spaced around the accelerator switch from positive to negative at a given frequency and accelerate the electrons near the speed of light. This is a concept that we have studied throughout Physics 30. The particles in the accelerator are also steered and focused on a proper path by magnetic fields, another concept we covered in Physics 30.
Scientists have used particle accelerators to study the origins of our universe and investigate the subatomic structure of the world around us. However, much more recently, many of these facilities have been dedicated to the sole purpose of advanced research in the field of medicine, in particular the search for a cure to COVID-19. This virus has thrown the world into a tailspin and changed everything. Daily life as we know it has been flipped on its head, making everyday tasks a serious health risk. An unlikely source for finding a cure has been unveiled, with serious research being proposed in many of the world's largest particle accelerators, including the Canadian Light Source in Saskatchewan, the Australian Synchrotron, and the Diamond Light Source in England. Researchers are using intense X-rays emitted by electrons to examine key proteins in the virus. The accelerators let scientists construct atomic-level, three-dimensional maps of the protein so they can develop drugs that bind to the virus, potentially preventing or treating the disease. In order to design a drug, you need to know what the protein looks like so the drug can attach to it. It's like designing a key for a lock. You need to know the dimensions of the keyhole. Techniques such as X-ray crystallography are used to obtain X-ray diffraction patterns of proteins. In order to obtain these signals and patterns, synchrotron radiation sources are ideal for macromolecular crystallography because they produce high-intensity X-rays with very narrow spread of wavelengths. X-ray radiation bright enough for the rapid analysis of protein structures can only be produced by a synchrotron light source. Knowing the atomic structure of the virus is like knowing how the enemy thinks. A 3D visualization of the building blocks of the structure at an atomic level would allow scientists to understand how the virus functions. Enzymes, the molecular machines that allow the virus to replicate, are key to this process. A drug that binds to an enzyme's active site would throw a chemical spanner in the works, blocking the virus's ability to replicate and limiting the spread of the disease. Although physics isn't typically associated with medicine in the body in the same way as biology or chemistry, particle accelerators and synchrotrons in particular offer a new and improved process to the development of vaccines and the understanding of viruses and proteins within the body. Although a vaccine is still a ways away from being developed, the research and understanding of COVID-19 that has been developed through the use of these systems is extremely valuable and help to gain a better understanding of our enemy.